Atomic radius can be thought of as the distance between the nucleus of an atom to its outer shell, where its outer electrons are found. And we're going to say that the general trend when it comes to atomic radius is, as we move from left to right, it's going to decrease. And as we move up any group, it's also going to decrease. Now, we do see some exceptions when it comes to atomic radius. So we're going to say here, when moving from 3D transition metals, so remember your 3D row is this row here. So when we're moving from 3D to 4D, 4D being this row here, we see a decrease in atomic radius. But when we're moving from 4D to 5D, 5D being this row here, it's very different. It's going to relatively stay the same. We're going to say that this exception to atomic radius is termed the lanthanide contraction. So remember, when comparing the atomic radius of the elements, we're going to say that the general trend is the one that we observe here. But transition metals, because of the presence of d orbitals, they're going to find an exception to this. And the exception lies between rows 3D and 4D of the transition metals. So if you want additional concepts dealing with atomic radius, make sure you take a look at our chapter dealing with periodic trends of the elements. In addition to atomic radius, I highly recommend looking at other periodic trends such as ionization energy, electron affinity, effective nuclear charge, and of course ionic radius. Whereas atomic radius has this general trend, when you're taking a look at ionic radius, we just look at the number of electrons to determine which one of the ions is greatest. Make sure you take a look at all of these periodic trends to get a complete look at the properties involved with elements and ions of the periodic table.